So the way I have designed this sessions, so this week and next week sessions is that this week I'm going to focus on the ORAN architecture mostly from the SMO and the CUDU side, and next week it's going to be on the RIC. And I like the split because I think RIC is equally important as a component. It definitely deserves its own session because there's so much that that can be talked about it. But this is how we see all the 10 ORAN working groups coming together. And as you can see, most of them are either talking about architecture or a specific interface that it deals with. And that's exactly what Open RAN as a concept or as a working group is. So Open RAN did come into existence because CSPs wanted it. They wanted more choice in vendor selection because primarily the RAN domain was dominated by only a few handful of vendors, not even handful, just a few of the vendors, mostly three or four vendors all across the globe, and that has kind of slowed down the innovation a lot in this space. So to bring openness and innovation to this, the CSPs come together to form the Open RAN Alliance. And then the whole industry has joined in, and now, as you all know, it has become a bigger phenomenon now. Um, Okay, so I'll keep coming back to this diagram. This is something that I absolutely loved, and I think probably you all might have seen this in I think all of the sessions that we have been through today. So and the reason for this is that it precisely tells what ORAN does and how it does it. The main thing to realize here is that ORAN doesn't want to replace 3GPP as a specification, but it just want to add on top of what is already in existing 3GPP specification. So all the gray ones here are 3GPP defined interfaces, the E1 interface, the F1 interface, and the UU interface. These are all 3GPP defined interfaces. In fact, there are a few more interfaces that goes out of the CU that I'll cover in the next one, which are also majority 3GPP interfaces. All the green ones are the ORAN interfaces. And these are the interfaces that are primarily defined by Open RAN. And then there is this interface, which is for future study, which is in discussion about if the O1 should be extended to the RU. So basically, should the SMO have a connection towards the RU? Because currently the RU is completely managed through the DU. So this is a work in progress or a thought in progress, and it has not yet specified. So if you look at it from the RAN perspective, right, there are a lot of components that have been recategorized here into how the Open RAN network would look like. And then there are some few new components that were not existing in the previous RAN network. So as you have seen before, the CU and the DU is something that used to be combined together in the traditional RAN space in what was known as maybe like something like eNode B, BTS. There are so many names to it. But basically, the same thing now has been split into two separate logical components, even physical sometimes. But all of them are, as you have heard, is going to be virtual anyways. So the CU, the DU, and the RU is something that we have seen probably in a different form of shape in the previous in the older RAN days. The newer things that have been added is the near real-time RIC or the RAN intelligence controller, uh, on the near real time and the non-real time basis, and a service management and orchestration framework. So there was a huge need for RIC in the industry, and this has been a gap that was there for a long time. It was kind of filled by a lot of third-party components, or even components that were supplied by the RAN vendors, but it was still not sufficient to cater all the challenges that we were seeing in the RAN space. Okay, so these two are kind of the new additions, and then below that is the O cloud layer. So we'll go a bit detail into this to find out what exactly this means, and how these components work with each other and what they actually do. So in today's session, I will try to go into the details of this. If there is time and if there is an interest, I could later on show that what we at VMware does in the overall stack as well. Okay. So, as I said previously, right? So this is a high-level functional diagram of what the specifications for ORAN are. Now, if we look at the interfaces side, and that this is what I was talking about, there are a lot of other interfaces that originates from the CU towards the traditional RAN side of the network, which are 3GPP interfaces. Okay, so if we look at from the top down, right? So there is an over interface that goes from the SMO towards all the components in the Open RAN, the near real time rig, the CU, the DU, and as I said, there is a discussion ongoing that should this be extended even to the RU. Okay, and then we have the O2 interface that goes to the O cloud, and an A1 interface that is primarily between the near real-time rig and the non-real-time rig. So the near real-time and the non-real-time rig talk to each other with what is known as an intent-based interface of A1. We'll go into details of this in our next session. Then there is E2 interface that goes from the near real-time rig to the CU and the DU. And this is, I find, is an extremely interesting interface that has enabled or opened doors to what probably was not possible in the conventional RAN before. And again, this is also one of the interface that we'll go into very detail in our next sessions, because this is all related to the rig side of the story. Okay, and then there are 3GPP interfaces, right? There's E1, there is X2, there is XN, there's F1, there's NG, and there is NGC and NGU. Now, we'll go into details of each of these blocks and try to identify or try to understand what exactly each of these components is supposed to do, and how it relates probably to the older version of the RAN that we know, and what uh, the additional functionalities that has been proposed by the ORAN Alliance. What value does all of that brings with this? Okay. There's also one more thing that is known as ORAN identified control loops, or ORAN defined control loops, and which is more to talk about how the RAN control loops should run, and also gives an idea of how the rig algorithms would work on the time scale granularity. Okay, so there is firstly a non-real time control loop that runs in the non-real time rig. This is a control loop that is 1 seconds or more latency working group control group. The second one is the near real time rig, which is usually in the order of tens of milliseconds. This takes care of the finer grain RAN RAN functionalities. And the third one is working on the DU level, which is the real-time control loop. So this would be embedded inside the DU, and we would have some control over it through the E2 interface from the near real-time link, but majority of that would be taken care by the DU itself. Okay, so you can see the granularities here for all of these. Okay. Um, Okay, now let's take a deeper look into what that architecture actually means from each component basis, and then we'll go into every component of the reference architecture. Just give me a moment. Sorry. Yeah. So to start with, what I would like to highlight is that I think Dr. Joe has also highlighted this, that open and reference architecture inherently assumes that everything is virtualized. So that's why you see there's an NFVI. So NFVI stands for Network Function Virtualization Platform. So this NFV platform provides the virtualization layer on top of the CTOS or off the shelf, common off the shelf hardware platform. What does that mean is that previously, if you have to deploy a RAN site, uh, to buy something from Ericsson. So they would manufacture the hardware in their factory. They would ship the hardware to whichever country it's going to get deployed to, and then it get installed. So imagine the whole supply chain complexity of getting hardware somewhere and then getting it um, delivered in some part of the world and then install it, right? It creates a lot of complexity. This gets even highlighted during the COVID pandemic when the supply chain was in a turmoil and the demand for work from home was on its peak, right? There's hardly anything that could have been done. The solution to that is there are off-the-shelf hardware that is available, like Dell servers, right? And we could use these servers to create a virtualized environment on top of which the network functions that are currently embedded inside these application specific hardware that the RAN vendors are selling can be completely virtualized into a form of a software application. And then that could run on top of the CTOS hardware. So that is basically the fundamental concept of running an open and virtualized network. Now, so when we talk of running that software components on top of a CTOS hardware, it's called virtualization of RAN. And when these components are interoperable and in compliance with the ORAN architecture, it is called Open RAN. And together, these two, we call this Open vRAN. So Open Virtualized RAN, wherein it is compliant with the Open RAN architecture. And along with that, it is also virtualized because there have been instances where Open RAN is, because this is a reference architecture, it is not a specification. So there are manufacturers who do manufacture Open RAN hardware, but it is not virtualized. It is still in the legacy format, right? Now, on top of that, we would have the CUs. Assumption is that the DU, the reference architecture says that the DU would run on the site, probably on a bare metal type of thing, but it doesn't have to be. This also can be, the DU also can be virtualized, right? Okay. And then the DU is separated into two logical components. One is control plane and the user plane. We'll get into the details of why it is done like that and what advantage of. Then there is the RAN intelligence controller on the near real-time component, which has its various functions embedded inside it. This is also a purely software component. And then the orchestration and management, which is the SMO component. This is also a software element to it. So if you look it from that perspective, right, the only hardware that we would need is a CTOS hardware to run any RAN software. Now, the beauty of this is that in the previous generations, when I used to work for 2G, 3G, and LTE, every time we had a technology change or even an upgrade between the technologies, right? Then when we move from 3G to 3G plus, like when we move from 3G to HSDPA or 2G to 3G and 3G to LTE, the way these networks were upgraded were extremely cumbersome. So imagine a network in a city like Manila, right? It would be very, very dense. You would probably have sites every 500 meters or so. Uh, and if not at a kilometer range, yeah. And then if you have to upgrade that, you need to physically go remove that 2G hardware and at the same time put the 3G hardware, get it up and running, get it up and running, and make sure that it's transmitting well enough to meet at least the minimum basic quality criteria. Uh, and and you have to do this on such a scale that the customer doesn't realize. I mean, I doubt any one of you might have realized when the technologies upgrade in that. Okay, I mean, you would realize when you see the signal on the phone, but you won't realize when it's actually happening, right? So this happens usually at the night. It's extremely cumbersome process. This used to be a very, very long process of upgrading. And the way it prevails is because, as I said previously, there were only few vendors that was controlling all of this. And it was a good business for them, right? It was a lot of good services, good hardware. They were making good money. Yeah, maybe that is a doubtful, but at least it was kind of an oligopoly between those CSPs. Now, with virtualized and open RAN, what this would lead to is that once you have deployed a CTOS hardware, and you need to upgrade it to a new technology or a new version, or even adding a new cell to that, it is all a software upgrade, basically, for which you don't need anybody to go to the site to rip out any hardware, put anything new. uh, all of that would be done through a software upgrade, just like the way we receive our upgrades on our phones or our laptops, right? So this is far more efficient in the long term, and this is probably the sustainable way of taking the telco upgrades and operations forward. Okay, now let's get into each of these components of what exactly those means, and understand what all constitutes of these functions that the open proposes. The first one is the service management and orchestration layer. So the service management and orchestration has three key components. One of them is a familiar one, which is the O&M or FCAPS manager. This is something that we had previously also in the RAN domain, which was the EMS or O&M manager of the RAN domain. Right. The two new components, however, are the non-real-time RIC and the O-Cloud manager. Now, the O&M and FCAPS manager for SMO is something that only takes care of the RAN domain. So what I mean by that is that there could be a lot of other domains or management domains inside these networks, right? And the 3GPP, sorry, the ORAN reference architectures, O&M or FCAPS manager only talks about the RAN domain management. However, the way it would get implemented probably would be a bit different, right? Because uh, it would make sense to integrate the other components as well into a wider O&M or SMO architecture, wherein you are also taking care of probably some components of core, transport, slicing as well. But that is not how ORAN defines it. And then that's the beauty of it. So it's a reference architecture. You can always use it and build on top of that whatever you think is best suitable, right? And then so what it does is it basically does the FCAPS management of the ORAN network functions uh, over the open interface. So if you remember previously, like the open interface is the one that goes from the SMO to the all the open RAN components, the CU, the DU, and as I said, this is going RUS and near apps manager is responsible for um, the olden days equivalent of PMCM FM and fault management. So performance as in how is it performing, getting some data, some analytics, some KPIs from it. Configuration management as in configuring it for how much say how much cell bandwidth there is, what frequency the cell to radiate on, and so on and so forth. Um, Fault management is if there is any fault, there's any alarms, and how to deal with that. File management is taking care of the software of all of this. Communication surveillance, as in if all of this is working fine. Also, it's known as the heartbeat. So making sure everything is up and running. Trace is a functionality that used to exist in the older days as well. Now that there is two line items at the end of it, which is the physical network function discovery and physical network function software management. So what physical network function means is the network function or a component that is not yet virtualized or not yet cloudified, right? So anything that is traditional is considered as a physical network function. So it has its own hardware, it has its own software embedded inside it, tightly coupled inside that box. So that is what a physical network function is. So the FCAPS manager would take care of that. So it's very similar to what we used to call the EMS in the older days. Okay. Now, as I said, it talks via the open interface, and there is also an open front hall management plane for RU, which runs through the DU. We'll get to that in the next slide. Now, the second component of the SMO is the OCloud manager. Okay, now this is a new component that has been proposed by the ORAN Alliance, and it has been proposed because, as I said, the inherent expectation is that everything is virtualized, right? And if everything is virtualized, when I say virtualized and cloudified, it is a slightly different understanding of how that component is built. When I say virtualized, it could be a component running in a virtual machine, in a virtualized format on a virtual machine. When I say cloudified, it's a component that is running as a containerized network function. So that's the distinction between cloud and virtualization. So cloud takes that a bit step ahead and containerize it into containerized software. But these terms are a lot of times used interchangeably, right? So the OCloud here means the NFV, the management of the NFV, the network function virtualization layer. And so the OCloud manager takes care of that, the underlying NFV layer. So all of that management, orchestration, and workflow of that layer is taken care by this. So what it means is that, of course, there's FCAPS again, the PMCM FM of that layer only. Uh, Plus, there is also discovery and administration of OCloud resources because these are dynamic resources, right? you can always upgrade a CTOS hardware. In a lot of times, even hot upgrade or hot swaps are possible, right? You plugged in a RAM, you plugged in hard drives. So a discovery of all of that, additional upgrades that have happened. Scale in and scale out of cloud. So what does it mean is that if the cloud infrastructure needs to grow out in either in any fashion, it is also controlled by the cloud manager. So what it means is that suppose you need more resources for a cell site, and the cloud can dynamically allocate those for that cloud component. Okay. Then there is software management also of the cloud, because there's also a software component to it. So the management of it, the upgrades and all of that. Plus the create, delete, and allocation of the allocated cloud resources, and the software management and deployment of also the resources itself, right? So there's platform, and then there are resources under it. So all of that is taken care by the cloud manager. Right. So this is a concept that has come from the IT side of the industry to the telco side of the industry. And the beauty of this is where the two good technologies merge. Uh, and as you would see in the future deployments, this would be the de facto way of deploying networks, because this is the most efficient way of deploying a RAN network. Right. Now, the third component in the SMO architecture is the non-real-time rig. Now, the non-real-time rig is so the primary goal of that non-real-time rig is to support intelligent RAN optimization. Okay. So it would have all the ML models, the enrichment information in the SMO side, and then it would provide that to the near real-time rig. The idea is that non-real-time rig would kind of be a centralized entity, and it would have the distributed near real-time rig across various cell sites in the network. Okay, and that's how we would bring the AI ML capabilities to the RAN domain. But this is something that has been missing from the RAN domain for a very, very long time. We so until even until later part of 3G, basic automation of the RAN workflows were also not possible, or also was not there. So there were engineers like me and a lot of others who used to write some type of code to automate some small components of this. And now all of that could be put together into a good good app on both the non-real-time and near real-time rig. We will get into the details of this, as I said in the next session. This is probably very interesting area, and an area where we would see a lot of innovation coming through. And this is an area where you definitely can look towards innovating and adding a lot of value to this ecosystem. So, if you talk from a higher level perspective, the non-real-time rig has two components. It has a framework, and then there are applications that run on top of this framework. So, we'll get into the details of the components of this framework and the apps and how they interact with each other, and how all of that data flow works in our next session. So I'll keep it precise for this one. Okay, so to collect it all together into the SMO, right? So this is a service-based architecture representation of all the components of how the SMO would look like, right? So Here is the RAN network function O&M services, which is the FCAPs that I was talking to you about, the FMPMCM. And as I say, it runs through the oven interface with the over nodes. So over nodes means the CUDU and the near real-time rig. And as I said, that there is an open front hall management plane interface through the DU, wherein from which um, these CMPM and FM would be collected uh, for the RU. On the OCloud management side, there is network function orchestrator and which takes care of the network function orchestration and the management function of this of the OCloud through the O2 interface, which is a separate interface that we have seen right on that was on the left side of that diagram. And then this is all the non-real-time components, which is that there is a service management and exposure, AIML workflows, and all of this. So we will get into the details of this in our next session. But this is how, if you look from the service-based discussion, right? So this is how the SMO would look like. The R1 actually is a interface under development. It's under discussion. I need to get a latest update on it if the specification has finalized. But the last I know, it was still under discussion, and most of the things were pre standard. So there are a lot of development that has happened, but most of it is pre standard. Okay, so this is how the service-based architecture of SMO would look like. Okay, so all of these discussions that we're doing is very aligned to how the Open RAN reference architecture or Open RAN defines the architecture. And as I said, it's a reference architecture, and the actual implementation might vary between how it is implemented by each of the vendors. Okay, now let's move on to the other component of the reference architecture, which is the near real-time rig. So again, it's a logical function that takes care of the near real-time optimization of the E2 nodes. And when I say E2 nodes, so if you remember, the near real-time rig connects to, we'll have the diagram again in a few slides. The near real-time rig connects through the E2 nodes, the E2 interface to all the other nodes, right? The CU, the DU. Those are called the E2 nodes. And the near real-time rig is something that is responsible for fine-grained action. So fine-grained action as in the actions wherein the control loops are in the order of milliseconds. Okay, a maximum up to 1 second. And this also hosts a lot of XApps, and it used the E2 interface again to collect this data. So probably one of the most, I say, most visionary or revolutionary interface that has been proposed by Oran Alliance is this E2 interface, because it is for the first time that the inner details of RAN are now accessible to anybody on the RAN on the programmability side. I have I have a diagram of how that evolution has happened, that I'll show it to you in the next session. And it's very interesting to see that these functionalities were not there in the RAN previously. And what all of that would bring to us is that we would have very intelligent RAN optimization that would be happening henceforward. So we would have all the good AI ML capabilities now percolating down even up to the DU. Okay. Now let's get into the CU. And as I said, we'll keep coming back to this diagram. I just love this. So the CU, or it is known as the control unit. So if you look from the traditional RAN perspective, right, this is something similar to what we used to call um, the the system module. Okay. So or something similar. It's not really apples to apples, but something similar to what's to be the system module, wherein you have the higher layers of the RAN stack taken into a component. Now, usually we would have a single CU software which would be logically split into the control plane and the user plane. Now, the reason why this split has happened is because now consider that you have two separate software components running, right? You have a software that is running for the control plane algorithm and a software that is running for the user plane algorithm. And take the same example of the load that I'm going to show you, and we'll look it from both traditional RAN perspective and this virtualized open RAN perspective, and you'll see the immediately why there is so much value to open virtualized RAN, and why it is actively being pursued everywhere. Now imagine that you have an area, for example, say there's a football stadium, okay, and there's a football match that is happening. So suddenly at this small location, you would have maybe 10,000, 20,000, 40,000 people gathering, right? And they're clicking photos, they're recording videos, and with all of these software components running on top of these phones now, like like Google Photos or Apple Photos, it would immediately start backing them up on the cloud, right? So imagine all of that data getting uploaded. Now this data is mostly on the user plane side, right? You need a lot of bandwidth on the user plane component, but not that control plane component needs to scale that far, that much, right? You want there's not a lot of signaling that is happening. There is, but not in the same proportion as the user plane. Right. Now consider that this is not open and virtualized. It is tightly packed into one hardware box that is put it on the side. Right. So what you would have to do in the traditional RAN space is that you would have to deploy both the control plane and the user plane capability to whatever is the maximum required, which here in case would be the user plane capability. So you need a lot of bandwidth. So you deploy a lot of sites, right? So you probably would waste a lot of control plane bandwidth, or control plane hardware, control plane um, components, just to make sure that you have enough user plane bandwidth available. Now, in come to the open and virtualized RAN space, as so we could even build an algorithm now with the help of RIC that it could dynamically provision these resources. So what I mean by that is that once it realizes that the user plane requirement is increasing, it would start spinning up the user plane instances. So it would dynamically start spinning up the user plane instances and instantiating that to cater for the bandwidth on the fly, and also for the control plane for whatever requirement it is. So you won't be wasting your resources. Definitely, you would need the underlying hardware for that, because but that would be significantly less than the hardware that you would have to put, considering that you are catering that with a tightly coupled older version of RAN, right? You would have to put a lot of sites around. Now, what you would have to do is you would have to consider the peak requirement of that stadium from the user plane and the control plane component separately, and then build a hardware around that, or build the hardware specification around that, and procure that hardware. So what does that mean is that once the stadium starts emptying, your user plane capacity would also start reducing in almost real time fashion. It won't happen real time. It probably would be the non real time rig that would trigger all of these. But you get the idea, right? That we don't need we don't need to over provision for things that are not going to happen right away, right? All of this can be dynamically provisioned when it is needed, and on the fly by the combination of this reference architecture. So by the combination of having the rig and the virtualized CUCP and the CUUP, we could dynamically scale all of this. Right. So that's the beauty of having it open and virtualized. Now, when we go to one component below, which is the DU. So the DU takes care of the lower layers of the RAN stack. The RLC, the MAC, and what we call the high physical layer. Dr. Joe has shared how the split between these layers is there. So Open Front Hall talks about a very specific 7.2 split. What it means is that 7 layers on top and two at the bottom in the RU is what the splits talks about. But these seven out of that, some are in the DU and some are in the CU. And then the bottom two are in the RU layer, which is the low-fi. That is what is known as the low-fi. So the RLC MAC and the high physical layer components are in the DU. Again, the DU, as I said previously, even though the reference architecture doesn't explicitly talk about, but in most cases, the DU is virtualized in the deployments, and it's a virtualized. It's also a software component that is deployed. Now, the beauty of this is that eventually you would be able to have procure a separate CU software and a separate DU software. So this could be two separate vendors that you could procure from, and all of this could be a completely separate vendor. So previously you have to buy all of this from one vendor, it's tightly coupled. You cannot do anything with it. Now you have the option of buying all of this separately from each of the vendors. The one thing to note here is that this is open interfaces that we're talking about, and that doesn't necessarily means it's plug and play, right? So it would definitely needs a component of integration testing between the various components before it goes to the field. So that's an additional component that we need to consider, that you won't have to in case you have to deploy a tightly coupled RAM. But the benefits that you get on top of that, it's significantly far better than the tightly coupled RAM, right? And as I said, RU is mostly a radio component, and it is something that has been there for a very long time. And when you say ORU or open RU, it basically means that the RU that is in compliant with the open front hall specifications. So any RU that is compliant with the open front hall specification is considered as ORU. This is going to be a physical hardware in because this is the component that would start radiating towards the UV. Okay, so this would be the component that would go on the tower and radiate towards the UV. So this probably you can say that the last mile connectivity component from the RAN perspective. Okay, now there are various deployment options. I think Dr. Joe also touched upon this, but let me also give my perspective on this. So when we talk about deployment option, I want to talk it from the Open RAN perspective, and also would try to give you a sense of how traditionally it used to be deployed, and what are the various ways this can be combined so that we could maximize whatever is currently available in the network. So traditionally, distributed RAN is a default way of deploying any RAN network, wherein cell site, or in terms of edge, it is called far edge. So cell site is where you would have both the CU and DU together. In traditional RAN, this was one component, one hardware inside that proprietary software, tightly coupled, that would deploy on the cell side. Now this was called the distributed RAN, wherein everything is on the cell side. Now, what because now Open RAN allows this to be split, we could have the DU on the side and a CU at an aggregate uh, location, right? So we could split this and we could bring the CU and the DU at two separate locations. Okay. This is also something called as hotel BTS in the LTE terms. So in LTE, especially in places like Korea, this used to be a way of deployment where they would have all the system units at one place, and the baseband units they would deploy at the cell sites. Uh, the reason why Korea was able to do this and not a lot of others is because the requirement between these, right? So now this line or this bandwidth is extended between these two sites. What does that mean is that you would need significant more bandwidth than previously needed because of the split of the CU and DU. And this is what was the factor that used to define. Now Korea had a lot of fiber available that time, so they could afford to split the system unit and baseband unit that time as well. And this, with the availability of fiber now everywhere, this is something that is possible. So we would have CUs aggregated at a site, and then the DUs would start distributing from there. Okay. The other way is that you could have both the CU and the DU at one place. So what would happen is that in wherever places you would have CU aggregate, right? You could also put the DU if you have enough bandwidth to support um, uh, the RU directly at the site. So nothing would run. So nothing would be there on site, but just the RU. This is typically called the cloud RAN, where everything is in the cloud. So this is defined as a cloud, and everything is in the cloud. Now, in most cases, what we would see is probably in hybrid implementation. So what is going to happen is that in most places we would have a CU on a cloud location, aggregated, and we would have a lot of distributed DUs across various cell sites. But on the same site, you would have some DUs serving the near locations. So at the same site, you would have some DUs also running. And remember, all of this is software components, so it really doesn't matter, right? So it's basically pieces of software running on some hardware. So it's not that complicated from that perspective. And all of that is connected back to one centralized location where you have core. Okay, now core is also mostly virtualized and sometimes even cloudified. Okay, so these are the deployment options for the RAN. I hope I'm not running. Okay, so why to do all of this, right? Why to get into all of this trouble was the as I said, the key component was to be able to reduce the OpEx in the longer run. You should be able to upgrade, maintain the network with the least possible operational overhead that you can. Software is the only way to go forward. The other is to reduce capex. Now, imagine when a network was upgrading from 3G to 4G, the hardware has to rip apart and they have to put a new hardware. Probably that one, even during components, right? So sometimes the vendors used to provide a new set of hardware. So upgrade of hardware. So you have to rip apart, even in the same technology, you have to rip apart the old hardware, put a new hardware. The older hardware is kind of wasted, right? You have to keep investing in that. Now, when you're working on a CTOS hardware, you have to invest once, and you could keep using that CTOS hardware and only upgrade the components that you would need to upgrade. Like, for example, you would need a faster NIC card. So you can just upgrade the NIC. But if the processors and the RAM and the hard disk is still good enough, you can still keep using it, right? Now, if the processor has become slower and a new processor is available, you could replace that processor, you could upgrade the RAM, you could upgrade the hard drive. You don't need to rip apart everything. So this is the advantage of having it open and virtualized. And as I said, it increases agility. It's going to bring programmability to the RAM, and that's how it's going to also make the ecosystem bigger. We have suddenly seen that there's so many players in the RAN side now uh, that previously it used to be. But let me be very open also about it, that it's not a straight path. It's not a really roses of bed. It's not a very smooth journey, because it's going to go through a lot of challenges, right? Because the RAN is very new to cloud. It has never been tested on cloud. Cloud is very new to the RAN side. There are security concerns, and then there are forces that are trying to keep the status as the same, because it serves their greater purpose. So considering all of this push and pull, right, we've seen a slow evolution towards the open RAN standard, and everybody kind of talks about virtualization of RAN, and probably every major RAN vendor currently supports Open RAN. We have seen that uh, almost all of the major RAN vendors have now kind of supported, a lot of them initially hesitantly, but now have started supporting Open RAN uh, reference architecture now. So that their systems would be built on ORAN compliant uh, hardware. Okay, so coming to the last slide of today's session, I think this was also one question that was asked uh, in the Q&A before I start that. In which countries do we see deployment? So there are 13 commercial launches all across, if you see. A lot of them in US. There's one in Peru. There's also a lot in Europe and in Japan. So a lot of people know Rakuten in Japan as one of the uh, key Open RAN player, but the the name that I would like to highlight is NTT Docomo. NTT Docomo has been at the forefront of Open RAN. They were a key part of the Open RAN Alliance, getting it formed as well. And they also tried bringing Open RAN in the LTE network as well. It didn't went successful for them, but they are at the forefront. They're pushing this. Uh, so they have something called Open RAN ORIC, they called Open RAN ecosystem, wherein a lot of other components are put together, and everybody can come and test the Open RAN. So there's a lot of Open RAN testing, field trials, deployments happening. Europe is where, and we are seeing a lot of governments getting interested in it. US government is interested, Indian government is interested, European government is interested. Singapore government is interested, I think, and then so many other governments are interested in exploring this, because they want to ensure that the key component of this economy of which is the CSPs also have the sustainable way to keep their networks. So the way I look at it is that we're going to see a lot of virtualization of and Open RAN getting deployed all across the world, and the share of Open RAN is going to go up eventually. And there would come a time when it would become like a de facto standard, wherein everybody would just assume that it is open.